Hi guys, welcome to Appsc AE free online classes. ఈ రోజు క్లాస్లో మనం స్ట్రెంత్ ఆఫ్ మెటీరియల్స్కి సంబంధించి టార్షన్ అనే టాపిక్ని చూద్దాం. ఈరోజు క్లాస్లో మనం చెప్పుకునే సిలబస్ ఏంటంటే అజంప్షన్స్, బేసిక్ ఫార్ములా ఆఫ్ టార్షన్, పవర్ ట్రాన్స్మిషన్ బై షాఫ్ట్స్ ఆఫ్ యూనిఫామ్ సర్క్యులర్ సెక్షన్స్, క్లోజ్ కాయిల్ స్ప్రింగ్స్, స్ట్రెయిన్ ఎనర్జీ ఇన్ సింపుల్ బీమ్స్ అండ్ షాఫ్ట్స్, సడన్ ఇంపాక్ట్ లోడింగ్, ప్రిన్సిపల్ స్ట్రెసెస్ అండ్ స్ట్రెయిన్స్, మోర్ సర్కిల్ ఆఫ్ స్ట్రెస్. ఎవరైనా మా ప్రీవియస్ వీడియోస్ చూడనట్లయితే లింక్ డిస్క్రిప్షన్లో ఉంది, వెళ్ళి చూడండి. ఈ వీడియోని కూడా లాస్ట్ వరకు చూడండి. మీకు నచ్చినట్లయితే లైక్ చేయండి, షేర్ చేయండి. First, we understand the concept of torsion. A shaft is said to be in torsion when equal and opposite torques are applied at the two equal ends of the shaft. Let's say this is a shaft. This is the length of the shaft. At the two equal ends, the torque is applied like this. Okay, due to the application of the torque at the two ends, the shaft is subjected to twisting moment. This causes the shear stresses and shear strains in the material of the shaft. Okay, what is meant by a torque? Torque is nothing but it's a product of force applied into the radius. If you observe the shaft from this direction, it seems to be a circle. From the circle, we find a radius easily. It is the center. This is called radius R. That radius is multiplied with the force applied, we get the torque value. Due to the torque, the twisting moment, the shaft is subjected to twisting moment due to the torque application. This causes the shear stresses and shear strains in the material of the shaft. A twisting moment em chestundi, shear stresses and shear strains anetivi a shaft లో జనరేట్ చేస్తుంది. ఓకే, నెక్స్ట్ వీ మూవ్ టు ద అజంప్షన్స్. ద డెరివేషన్ ఆఫ్ ద షియర్ స్ట్రెస్ ప్రొడ్యూస్డ్ ఇన్ ఎ సర్క్యులర్ షాఫ్ట్ సబ్జెక్టెడ్ టు టార్షన్. దిస్ ఈస్ ద డెరివేషన్ యాక్చువల్లీ వీ డూ ఫర్ ద ఫార్ములా ఫర్ టార్షన్. సమ్ బేసిక్ assumptions are made while doing the derivation. What are the assumptions we can see now? The first one is the material of the shaft is uniform throughout. షాఫ్ట్ మెటీరియల్ అనేది మనం యూనిఫామ్ అని అస్యూమ్ చేసుకుంటున్నాం. సెకండ్ వన్ ఈజ్ ద ట్విస్ట్ అలాంగ్ ద షాఫ్ట్ ఈజ్ యూనిఫామ్. మనము టూ ఈక్వల్ ఎండ్స్ దగ్గర టార్క్ అనేది అప్లై చేస్తున్నాం. డ్యూ టు ద టార్క్ ఇట్ ఈస్ ద షాఫ్ట్ ఈజ్ సబ్జెక్టెడ్ టు ట్విస్టింగ్. దట్ ట్విస్టింగ్ ఈజ్ సేమ్, ఇట్ ఈజ్ యూనిఫామ్ త్రూ అవుట్ ద షాఫ్ట్. ఆ ఎంత లెంత్ ఉంటుందో అంత లెంత్లో ఆ ట్విస్ట్ అనేది సేమ్గా ఉంటుంది. And the third one is the shaft is of uniform circular section throughout. We can assume the shaft is uniform circular section. It is not a rectangular section, it is not a triangular section, it is not a square section. We can assume it as uniform circular section. The cross section of the shaft which are plane before the twist remain plane after the twist. ట్విస్ట్కి ముందు ట్విస్ట్కి తర్వాత క్రాస్ సెక్షన్ ఆఫ్ ద షాఫ్ట్ అనేది సేమ్గా ఉంటుంది, ప్లెయిన్గా ఉంటుంది. అంటే ఇది కర్వ్డ్గా అవ్వదు. ఆఫ్టర్ ద ట్విస్ట్ అయిన తర్వాత కర్వ్ ఏం అవ్వదు. ఎలా ప్లెయిన్గా ఉండిందో బిఫోర్ ట్విస్ట్, ఆఫ్టర్ ట్విస్ట్ కూడా అలానే ఉంటుంది. ద రేడియై విచ్ ఆర్ స్ట్రైట్ బిఫోర్ ద ట్విస్ట్ రిమైన్ స్ట్రైట్ ఆఫ్టర్ ద ట్విస్ట్. బిఫోర్ ట్విస్ట్, ఆఫ్టర్ ట్విస్ట్ తర్వాత రేడియై అనేది మనకు స్ట్రైట్గానే ఉంటుంది. ఓకే, ఇట్ డస్ నాట్ turn into a curve. It just as straight only. These are the assumptions we made for the derivation of a torsion. Next we move to the basic formula of torsion. The basic torsion formula is given by this. Based on these diagrams. This diagram is before twist, this diagram is after twist. This is the shaft before twist. The cross section of the shaft is like this before twist. After twist, it is a center line. CD is a center line of the shaft. The center is changes to CD to CD dash. Some angle is made, that is called phi. okay, due to the application of the torque. That changes the cross section also. The OD is changes to OD dash. It made an angle theta from the horizontal. That theta is called as angle of twist. The basic formula is given by based on these diagrams only, before twist and after twist. Okay, before application of the torque and after the application of the torque. Before application of the torque and after application of the torque diagrams only, we have to derive the equation or formula for the torsion. The terms involved here are tau by r is equals to c theta by l is equals to q by r is the formula. Okay, tau is the shear stress induced at the surface of the shaft due to the torque T. T మనం ఎంత టార్క్ అయితే అప్లై చేస్తున్నామో దాని ద్వారా షియర్ స్ట్రెస్ అనేది ఆ సర్ఫేస్ మీద, ఆ షాఫ్ట్ సర్ఫేస్ మీద ఇండ్యూస్ అవుతుంది. దాన్ని ఏమంటున్నామంటే షియర్ స్ట్రెస్ టౌ అంటున్నాం. ఓకే, దట్ ఈస్ కాల్డ్ టౌ. R is called the radius of the shaft. C is called the modulus of rigidity of the material of the shaft. In some textbooks, the modulus of rigidity is given by G. In some textbooks, C. In some textbooks, N. Whatever may be the symbol, they denote the same, which is modulus of rigidity of the material only. Theta is the angle of the twist, we can see from this diagram, and L is the length of the shaft. This is the length of the shaft. Q, small q is the shear stress induced at a radius r. At small radius r, okay, the shear stress induced is small q. If capital R, the shear stress is induced is tau. Next we move to power transmission by shafts of uniform circular section. మనకు టార్క్ ఎక్స్ప్రెషన్ తెలిస్తే మనము పవర్ ట్రాన్స్మిషన్ అనేది కనుక్కుంటాం. ఎందుకంటే యాక్చువల్ ఫార్ములా ఫర్ పవర్ ట్రాన్స్మిషన్ ఈజ్ పవర్ ట్రాన్స్మిషన్ ఈజ్ ఈక్వల్స్ టు 2 pi nt divided by 60. This 2 pi n divided by 60 is omega into t. This t is mean torque transmitted in Newton meter. Omega is angular speed of shaft. N is the rotation per minute of the shaft, RPM of the shaft. This is the basic power formula. But in this omega, I find by using 2 pi n by 60 omega value, but tau is not known to me. For the different sections it may change, so we have to calculate uniform circular sections, isn't it? For the uniform circular sections, we have two types in the circular sections. One is solid and another one is hollow. For the solid case, the torque transmitted by a circular solid shaft is given by pi by 16 into tau into dq. But we have to calculate the power transmission. So power P is equals to pi by 16 into tau into d cube. This is the t value multiplied by omega. Omega value will be 2 pi n by 60. The next case is the torque transmitted by a hollow circular shaft. For the hollow case, a torque value will be pi by 16 into tau into d naught power 4 minus d I power 4 divided by d naught. This is the formula for torque. But I need power transmission, so power transmission is equals to pi by 16 into tau into d naught power 4 minus di power 4 divided by d naught into omega. Omega will be 2 pi n by 60. Okay. Next we move to the springs concept. Springs are the elastic bodies. That means if you apply a load on the springs, after removal of the load, the springs are attain its original position. Okay, which absorb energy due to resilience. What is meant by resilience? The total strain energy stored in a body is commonly known as resilience. In other words, the capacity of a strained body for doing work on the removal of the straining force. వర్క్ చేసేదానికి స్ట్రెయిన్డ్ బాడీకి ఉన్న కెపాసిటీని ఏమంటున్నామంటే రెసిలియన్స్ అంటున్నాం. ఓకే, ఐ హోప్ ద టర్మ్ రెసిలియన్స్ ఈజ్ క్లియర్. ద అబ్జర్వ్డ్ ఎనర్జీ మే బి రిలీజ్డ్ యాజ్ అండ్ వెన్ రిక్వైర్డ్. అబ్జర్వ్ ఎనర్జీ అనేది కొన్నిసార్లు తీసుకుంటుంది, కొన్నిసార్లు అవసరమైనప్పుడు వదిలేస్తుంది. A spring which is capable of absorbing the greatest amount of energy for the given stress without getting permanently distorted is known as best spring. That means if I apply greatest amount of the energy for the given stress. Given stress means this is a stress. For this stress, I apply maximum amount of energy is I apply, but the spring does not getting a permanent distorted. That means if the body is plastic, if you give a load, if it is distorted, it cannot attain its original position after removal of the load. But it is a elastic body. If you remove the load, it get its original position, so it doesn't get permanently distorted. So for the given stress, it take maximum energy, then the spring is called as best spring. Spring is called as best spring. There are two types of springs. We have one is laminated or leaf springs, another one is helical springs. I can show what is a laminated or leaf spring. This is a laminated or leaf spring. We can observe this type of spring in the tractors, in the trolleys, in the buses, in lorries also. We can observe these type of springs. Another type of spring is helical spring. Helical spring is again classified as open coiled helical spring, close coiled helical spring. Open coiled helical spring and the close coiled helical spring. In our syllabus, we have a close coiled springs only. Close coiled springs itself, close coiled helical springs. We can see in a detail. Close coiled helical springs are the springs in which helix angle is 0. That means helix angle is 0, is very small. In another words, we can tell pitch between the two adjacent turns. That means this is one turn, this is one turn, this is one turn, this is one turn. The pitch, this is the distance between the turns, this is called a pitch. The pitch is also very small for the close coiled helical springs. A close coiled helical spring carries axial load. We can hear the word axial load many times. The load passing through the axis, we call it axial load. As the helix angle in case of close coiled helical springs are small, hence the bending effect on the spring is ignored, and we assume that the coils of the close coiled helical spring are to stand purely torsional stresses. What here tell a helix angle is very very small. Due to that, bending effect is neglected. Effect is neglected. మనం ఇక్కడ బెండింగ్ ఎఫెక్ట్ లేదు కాబట్టి మనం ఏం అస్యూమ్ చేసుకుంటున్నామంటే ఆ క్లోజ్ కాల్డ్ హెలికల్ స్ప్రింగ్స్ అనేటివి దే విత్ స్టాండ్ ఓన్లీ ఫర్ ప్యూర్లీ టార్షనల్ స్ట్రెసెస్. ఓకే, వై బికాస్ ద బెండింగ్ స్ట్రెసెస్ ఆర్ జీరో. Why? Because the bending effect is not there. That's why the bending stresses is zero. They withstand only for the purely torsional stresses. Okay, we can observe here. This is the close coiled Helix Spring. Okay, next we see the derivation for close coiled helical spring, but the derivation is not needed. I just give a formula. Please remember the formulas. Those formulas sufficient to solve the problems in the examination. Let D is the diameter of the spring wire, P is the pitch of the helical spring, N is the number of coils, R is the mean radius of spring coil, W is equals to axial load on spring, C is the modulus of rigidity, tau is maximum shear stress induced in the wire. Theta is angle of twist in spring wire. Delta is deflection of spring due to axial load. L is the length of the wire. I give three formulas for the closed coil springs. One is maximum shear stress induced in the wire, and the second one is deflection of spring due to axial load, and the third one is stiffness. Okay, first expression for maximum shear stress induced in the wire is given by tau is equals to 16 W. This is the axial load. R is the radius, mean radius, pi into d cube. D is the diameter. Okay, expression for deflection is delta is equals to 64 W R cube En divided by C d power 4. N is the number of coils. We can do an experiment on closed coiled helical springs in the laboratory of strength of materials. They give n value as 5. For some cases n value is 6. We can count because how many turns it have. Based on the turns only we get the number of coils. Okay, n is the number of coils, and the expression for the stiffness is given by W by delta. If we substitute W value here, the W value is there, so W get cancelled out. We get K value as C d power 4 by 64 R cube N. This is the formula for stiffness of spring. Please remember these formulas. Those are very sufficient for our examination. Next we move for the strain energy. Whenever a body is strained, the energy is observed in the body. Okay, the energy which is observed in the body due to straining effect is called as strain energy. Straining effect వల్ల బాడీ అనేది ఎనర్జీని అబ్జర్వ్ చేసుకుంటే ఆ ఎనర్జీని స్ట్రెయిన్ ఎనర్జీ అంటాం. ఆ స్ట్రైనింగ్ ఎఫెక్ట్ దేని వల్ల వస్తుందంటే 3 కేసెస్ ఉన్నాయి మనకు. గ్రాడ్యువల్లీ అప్లైడ్ లోడ్ కేస్, సడన్లీ అప్లైడ్ లోడ్ అండ్ లోడ్ విత్ ఇంపాక్ట్. But in our syllabus we don't have gradually applied load. We have only suddenly applied load or load with impact. Gradually applied load is we can observe from compressive loads, because for first we apply 4 tons and we can apply 10 tons. Gradually we can increase the load. Okay, a suddenly applied load is once we can apply a huge amount of load on the body. Load with impact, if you add load suddenly from some height, it gets some impact on the body, that is called as load with impact. Hence the strain energy will be stored in the body when the load is applied gradually or suddenly or with an impact. ఆ 3 కేసెస్ వల్ల స్ట్రెయిన్ ఎనర్జీ అనేది మనకు బాడీలో స్టోర్ అవుతుంది. ద స్ట్రెయిన్ ఎనర్జీ స్టోర్డ్ ఇన్ ద బాడీ ఈజ్ ఈక్వల్స్ టు ద వర్క్ డన్ బై ద అప్లైడ్ లోడ్ ఇన్ ద స్ట్రెచింగ్ బాడీ. strain energy stored in the body is equals to work done by the applied load. Please remember this point, because we derive the equations based on this one, that is strain energy is equals to work done. Okay, the first case we can see, load is applied suddenly. We don't have a gradually applied load, we have only two cases, that is first one is suddenly applied load, second one is load with impact. Let P is load applied suddenly, L is length of a bar, A is area of a cross section, V is volume of a bar, E is Young's modulus. Okay, X is extension of a bar, sigma is stress induced by the suddenly applied load, U is strain energy stored. I provide 3 steps for 2 cases. The first one is work done by the load is equals to load into extension, P into X. But the extension value is PL by AE. From we can learn this formula from stress strain concept. Okay, PL by AE. Maximum strain energy stored in the body is given by U is equals to sigma squared by 2E into volume. Volume is area into length. If we equate strain energy with work done, that is P into PL by AE. Okay, let's say, please wait, I can provide a derivation for this case. The next case, I just give a overall about that. I used to equate work done with maximum strain energy stored, that is sigma squared by 2E into AL is equals to PL by AE. Okay, this E cancelled out, this L is cancelled out. We get this formula. Okay, if you solve this, the stress value will be 2 times of P by A. I hope this is clear. After obtaining the value of stress value, the values of extension and the strain energy stored in the body may be calculated easily. If you get this value, stress value, the strain energy value and the extension X value, X is equals to PL by AE. This extension value and the strain energy U value we can get easily. Okay, next we move to this another case. When the load is applied with an impact, first we see the suddenly load. If we can see load with impact. P is load applied, not suddenly, load applied, or load with impact. L is length of the bar, A is area of the cross section, V is volume of the bar, E is Young's modulus, H is height through which the load is dropped. This is H. Delta L is extension of the rod. This is the extension. Sigma is equals to stress induced in the rod due to impact load. U is strain energy stored. Okay, the load is applied. The collar is moved to plus delta L distance. Okay, we can see work done by the load is equals to load into distance removed, P into H plus delta L. This is H plus delta L is the distance moved. Strain energy in this stored by the rod is equals to sigma squared by 2E into volume A into L. If you equate this, for the delta L value we can substitute PL by AE, but P by A is stress, so sigma L by E. We can substitute this, we get a quadratic equation, and we can solve a stress value in, we get a plus or minus, but we consider only the positive value only. That is, stress sigma is equals to P by A 1 plus under root of 1 plus 2AEH by PL is the formula for stress. Based on this derivation only, some conclusions are made. What are those conclusions? We can see now. If delta L is very small with compared to H, so delta L is very small, then delta L will be neglected. Then the work done will be P into H. We can equate work done with strain energy. We get stress as stress is equals to under root of 2EPH by AL is the formula for stress. In the next case, if H is equals to 0, we can put in the work done H value is 0, so the work done will be P into delta L. Then the stress value will be 2P by A, which is the case of suddenly applied load. Once the stress sigma is known, the corresponding instantaneous extension and the strain energy can be obtained. If you know the stress value, if you know the sigma value, we can easily calculate the extension value and the strain energy U value and extension delta L value in this case. Next we move to the another topic, that is principal planes and principal stresses. What is meant by a principal plane? The planes which have no shear stress are known as principal planes. షియర్ స్ట్రెస్ అనేది 0 ఉంటే ఆ ప్లేన్స్ని ఏమంటున్నామంటే మనం ప్రిన్సిపల్ ప్లేన్స్ అంటున్నాం. హెన్స్ ద ప్రిన్సిపల్ ప్లేన్స్ ఆర్ ద ప్లేన్స్ ఆఫ్ జీరో షియర్ స్ట్రెస్. దీస్ ప్లేన్స్ క్యారీ ఓన్లీ నార్మల్ స్ట్రెస్. షియర్ స్ట్రెస్ అనేది 0, సో దే క్యారీ ఓన్లీ నార్మల్ స్ట్రెస్. The normal stresses acting on a principal plane are known as principal stresses. ప్రిన్సిపల్ ప్లేన్ మీద యాక్ట్ అయ్యే నార్మల్ స్ట్రెసెస్ని ఏమంటున్నాం? ప్రిన్సిపల్ స్ట్రెసెస్ అంటున్నాం. ఓకే, ప్రిన్సిపల్ ప్లేన్ అంటే చూసాం, ప్రిన్సిపల్ స్ట్రెసెస్ అంటే చూసాం. ఆ స్ట్రెసెస్ని ఏ విధంగా కనుక్కుంటామో చూద్దాం. వీ హ్యావ్ 2 methods we determine the stresses. The first method is analytical method and the second one is graphical method. In our syllabus we have graphical method, that is Mohs circle. Mohs circle of stresses is the graphical method. If you need analytical method, please go through R.K. Bansal textbook. Strength of materials by R.K. Bansal textbook is sufficient for our examination. So we can see the Mohs circle method. Mohs circle method. Mohs circle is a graphical method of finding the normal, tangential and resultant stresses on an oblique plane. Mohs circle will be drawn for the following cases. మనం Mohs circle ద్వారా ఏం కనుక్కుంటున్నాం? నార్మల్ టాంజెన్షియల్ స్ట్రెసెస్ని కనుక్కుంటున్నాం ఫర్ ఆబ్లిక్ ప్లేన్. ఆబ్లిక్ ప్లేన్కి లెట్స్ సే దిస్ ఈజ్ ఆబ్లిక్ వన్. ఓకే, ఫర్ దిస్ we can calculate normal and tangential stresses by using the Mohs circle method. It's a graphical method. We can plot the Mohs circle in the graph paper. In this case we have 3 cases. In this method we have 3 cases. The first one is a body subjected to 2 mutually perpendicular principal tensile stresses of unequal intensities. Remember, the intensities are unequal, they are not same, they are differ. The intensities are differ, but in 2 mutually perpendicular directions the principal tensile stresses are acting on a body. This is the first case. The second case is a body subjected to 2 mutually perpendicular principal stresses which are unequal and unlike. They are not same, the intensities are unequal and they are, let's say, this is a case, first case. This is a case, first case. This is a first case. The second case is If it is compressive, this direction, this one is tensile. Unlike kada, unlike అంటే one direction లో tensile ఉంటే another direction లో compressive ఉంటుంది ప్రిన్సిపల్ స్ట్రెసెస్ అనేటివి. అంటే థర్డ్ కేసు వచ్చేసరికి a body subjected to two mutually perpendicular principal tensile stresses accompanied by a simple shear. This is the body, this is the tensile stresses in two perpendicular directions, and it is accompanied by a simple shear. This is a shear. This is the another case. If you plot Mohs circle for these cases, how they look and how we find normal and tangential stresses by using the Mohs circle. In the first case, a body subjected to two mutually perpendicular principal tensile stresses of unequal intensities. For this, I draw a figure like this. They are tensile stresses. They are perpendicular to each other and they have unequal intensities. If it is sigma 1, it is sigma 2. Sigma 1 is not equals to sigma 2. The intensities are not equal. Okay, if you plot Mohs circle on the graph paper, this is the Mohs circle we get. Mohs circle we get. From this figure, I use it to find normal stress and tangential stress. Normal stress is given by AD. This distance in the graph paper we get normal stress, and ED distance will give tangential stress. The next case is a body subjected to two mutually perpendicular principal stresses which are unequal and unlike. This is a body, two mutually perpendicular principal stresses. One is a tensile, let's say, another one is compressive. This is tensile, this is compressive. Like this, a body is subjected to principal stresses. For this case, if you plot Mohs circle on the graph paper, the Mohs circle will look like this. From this, we can find normal stress as AD distance as normal stress and ED distance as tangential stress. The next case, we see a body subjected to two mutually perpendicular principal tensile stresses. This is a body, these are the tensile stresses. These are tensile stresses and accompanied by a simple shear. This is a shear. Simple shear. If you plot Mohs circle for this, the Mohs circle look like this. The distance AD it gives normal stress and ED give tensile stress. I hope the class is helpful for your preparation. In the next class, we will see another topic. Thank you.